Welcome AP students. In today's video, I will show you how to answer design your own experiment type AP free response questions. First, I'm going to show you an example problem and an example solution, my solution. Then I'm going to evaluate that solution, show you how these types of questions are graded, as well as discuss some kinds of pitfalls that you might encounter and lose points on. And then I'm going to move on more generally to techniques of linearizing curved data trends in data analysis. So let's begin. This problem is Mechanics 2012, number 2. And before I begin, I just want to point out that for me personally, I find that my weakness in these types of problems is that I tend to want to say too much. And you've got to be careful of that. Obviously, you've got to also be careful of not saying enough. But saying too much is also a problem because, as you know, these tests are timed. So in this particular kind of question, you would have 15 minutes to answer it. So if you give too much detail, you may not finish and you may lose points because you didn't get to certain parts of this question or other questions. So that being said, while I solved this, I timed myself and I was cognizant of that. And so I put the times of approximately how long it took me to answer each question for your reference. Okay, so here's the question. You are to perform an experiment investigating the conservation of mechanical energy involving a transformation from initial gravitational potential energy to translational kinetic energy. You are given the equipment listed below, all the supports required to hold the equipment, and a lab table. On the list below, indicate each piece of equipment you would use by checking the line next to each item. So here's my solution. So this is what I checked off initially. I checked off the track, the cart, the meter stick to measure off distances, and a stopwatch. When I did this, I actually forgot to check off electronic balance. So interesting, you know, it's easy to leave something off, but you do need that because remember, mechanical energy has kinetic energy and potential energy both have mass in them, so we have to record the mass. At this point, just reading and checking off took me 30 seconds. Okay, so then the next question. B, outline the procedure for performing the experiment. Include a diagram of your experimental setup, label the equipment in your diagram, also include a description of the measurements you would make and a symbol for each measurement. There are a lot of little technical instructions here that a lot of students lose credit on. For example, the diagram, a lot of students draw the diagram, but look at this, label the equipment in your diagram. So when you draw this, this may obviously be a cart for you and this a track, but they told you to label. So you better put track there, cart. I put support, that's probably not necessary. I put the table. And then what I did is I also labeled the height. It didn't tell me to do that, but it's a good idea to list whatever distances you measure or determine in your experiment right in your diagram, and that makes things clear later. Then what I'm going to do is measure off a distance D of 1 meter along the table. So there's my setup. Again, the procedure, you've got to be as brief as possible, yet still be complete. So there's no set rule, but I think if you're getting on to steps 5, 6, 7, 8, you may be providing too much information, spending too much time on the question. Also, notice it says outline a procedure. My take on that is you don't need complete sentences. So you might notice the grammar here might be a little broken. So the first thing that I write is using the electronic balance, measure the mass M of the cart. And you might just say, measure the mass of the cart. You would not get credit. You will see that later. What you want to do is every time you state what kind of measurement to make, you want to label what or say what you're going to use. Now, obviously, we know balance is used. What else are you going to use to measure the mass? but you have to actually say it in these questions. So using the electronic balance, obviously not the stopwatch to measure the mass, but you still say it. And then also, you're going to see later, you want to give a symbol for the mass M. Obviously, we use mass M all year, but you want to go ahead and state that right in the question. See here, it says make a symbol for each measurement. So there's my symbol for the mass. Next thing, I'm going to use the support. Using a support, place track at an incline. Notice I left the word the out again. Again, you don't have to be perfect with your grammar. And maybe I didn't even need that, but I put it there anyways. So then, next thing, I use the meter stick, again, to measure the distance d 1 meter along the floor. So again, I'm saying what I'm using to measure, I don't say just measure d, okay, or measure distance. I have to say, I'm using the meter stick, and then I don't just say measure distance, I measure distance d, right? I am, where is it? Using the symbol again. Step 3, I place the car near the top of the incline and use a meter stick to measure the height h of the table. Again, meter stick to measure height h. And then 4, release the car and use stopwatch to measure time t. So again, I'm stopwatch, measure time t. The thing I use, what I'm measuring, and a symbol. Of the cart to travel the d equals 1 meter along the floor. At this point, I spent 5 minutes and 10 seconds, so I'm in good shape time-wise. Okay, let's move on to the next part. So I have the question here again, because so you could, you don't have to rewind in the video to see, but it's right here for us. So the next step, give a detailed account of the calculations of gravitational potential energy and translational kinetic energy both before and after the transformation in terms of the quantities measured in part B. So the gravitational and kinetic before and after. So what I did is I labeled those mechanical energies. So mechanical energy initial was kinetic energy initial and gravitational energy initial. Now, of course, at the top of the incline, when I'm holding that cart up there is no kinetic energy. So I crossed that off, and then, oops, I left off a little something here, plus UG. And then, so all that's left is the MGH. Okay, so again, in terms of the quantities measured in part B, right, MGH. Then the mechanical energy final is also kinetic and gravitational, but this is at the bottom of the hill, bottom of the incline. So now the gravitational is 0, I crossed that out, leaving me just 1/2 mv squared. That is not in terms of the quantities measured in part B, right? I never measured v. I measured distance and time. So I substitute out velocity as distance over time, and I square everything there. There's the mechanical energy final in terms of the given measurements of part B. At this point, I spent 6 minutes and 48 seconds, so I am very much making good time on this question. All right, next, after your first initial trial, your calculations show that the energy increased during the experiment. Assuming you made no mathematical errors, give a reasonable explanation for this result. So not only do you have to be able to design experiments, show that you can think in terms of science, how to capture data to come to some scientific conclusion, you also have to be able to demonstrate to the college board that you know how to interpret data and how to write effective conclusions. So we did this in our physics classes. Remember, all year we were writing conclusions. And I said, when you write a conclusion, you have to come up with sources of error. One, that are data-based. You can't say human error, I made a mistake. Okay, that's not valid. Even they say it here. So assume no mathematical error. So you can't say, oh, I must have punched something wrong in a calculator. No, we're assuming you did everything right with the numbers. What in your experimental technique, what in your experimental procedure is flawed? And then you cannot say things that are inconsistent with your error. So for example, in this they said the energy increased. In other words, at the bottom of the hill, we had more kinetic energy than we had potential at the top. You cannot say friction, right? That is a reason for the energy to decrease. So it has to be some kind of factor that's within the experiment, not human error. And by the way, it could be things that humans do wrong. You could say, oh, I lifted the mass too high or whatever. But so you can't, it's not that you can't say anything about what humans do in experiments. Of course, we're part of the experiments. So we might have made a mistake, but you need to quantify exactly. You can't just throw out the word human error and say that you're done. Okay, you have to say exactly what did you do wrong? Okay, and why did it lead to an increase in the energy? Okay, so here's my explanation. Again, I tend to say too much in my opinion, so I'm always cognizant about wasting too much time. But here's my explanation. One possible reason that was that I might have accidentally moved the car a little higher up the hill after I measured H, but before I released the cart. Thus, mechanical energy initial was actually higher than my calculated value. So then I observed ME initial was less than ME final because I artificially thought it was lower than what it truly was because I lifted it higher. At this point, we're 9 minutes and 32 seconds in. And then part E. On all the trials, your calculations show the energy decreased during the experiment. Assuming you made no mathematical errors, give a reasonable physical explanation for the fact that the average energy you determined decreased. Include references to conservative and non-conservative forces as appropriate. So remember, a conservative force, you may not remember this, but it's like gravity, spring force, electrical force. So those are conservative forces that you tend to get back any work in a conservative force. If you move an object one way, and you know, you put work in, you get it back when it moves the other way. So a non-conservative force is one that you can't get the energy back from when you create work. So that's a little background. I don't want to get too much into it and spend too much time on it at this point. But this is my explanation. So why did the energy decrease? In other words, we had less kinetic energy. I said at the end, as the car rolled, it was subject to the non-conservative force of friction. Then I drew a little diagram here showing that the force of friction was backwards while the motion was in the forward direction. So using the work energy theorem, delta K equals work net, which is force times distance cosine of 180 here, right? These are 180 degrees apart. I find that the work net is negative and therefore delta K is negative. Thus, kinetic energy decreased as the car rolled along the floor. And so I'm 12 minutes in, so I finished with time to spare. Okay, so, all right, now what I want to do is show you the answer key. I have it printed out and we can grade what I did. So let me flip this down. Okay, so in part A, hopefully this is visible. It's very small. I see it on the camera here, but hopefully on YouTube it'll show. So in part A, 1 point for choosing the meter stick and stopwatch. Regardless of what else is checked, I got lucky. I forgot to check the electronic balance, and it doesn't matter. As long as I checked the stopwatch and meter stick, I got the 1 out of 1 on part A. So that's good. 1 out of 1. Okay, B, for a procedure that indicates the height needed to calculate the gravitational potential energy. So I did that. I said place the car and use the meter stick to measure the height from the table. So I got that 1 point. Okay, the next point, for a procedure that indicates distance and time measured to calculate velocity. So here I measured my distance 1 meter along the floor, and then I used this, I used the stopwatch to measure the time t. So that's both the distance here and the time here in step 4. So I got the 2nd point. And then for a diagram and a clear indication of the height measurement, see, they didn't say that in the question that you had to include the height measurement. Yeah, It didn't say that about the diagram, and yet they wanted that. So like I say, whenever you can, put in distances in your diagram to indicate where they are in the procedure, okay? And then for a diagram and a clear indication of the distance measurement. So here's my diagram and a clear indication of the distance measurement. Okay, so it looks like I got 4 out of 4 on that question. Okay, I'm going to skip these other examples. We could talk about them in a little bit, but I want to move on to the next part of my question. So part E or C, sorry. First thing, 1 point for a clear indication of the initial potential energy of the system, which I have. The initial is mgh. And then 1 point for a clear indication of the final potential energy of the system. I crossed it off at 0. That's the final potential energy. So I think I get that point as well. For a clear indication of the initial kinetic energy of the system, well, here's the initial kinetic energy. I indicate that it's 0. So I think I'm up to 3 points now. And then for a clear indication of the final kinetic energy of the system, yes, I have 1 FmV squared. Okay, so that's the 4th point. And then for a correct calculation of the instantaneous velocity of the system, which I had as d over t at the bottom. Now that's the average velocity along the floor, which happens to be the instantaneous velocity at the bottom of the hill, assuming that it rolls with without a loss of mechanical energy. So I think that that is the instantaneous velocity here, the average velocity along the floor. So I'm thinking I get the 2 out of 2 there also, leaving me 6 out of 6 on this calculation portion. Okay, so then the next part, the errors. So that's here, D. So one reason why the mechanical energy in the beginning, it increased. In other words, why would we possibly have more kinetic energy at the bottom? So the answer that they're looking for is, well, here's how they give you points for identifying a reasonable cause of the increase in energy. That's reasonable to say that you accidentally put the car too high. So then when it got to the bottom, it had more kinetic energy than you would anticipate. So I would say that's one. And then for a reasonable explanation related to the cause identified. So you can't just say, I put the car too high, right? So you have to then, so that would just be identifying a reasonable cause. Well, what would the putting the car too high do? Right? You can't say, car too high, done. No, you have to say more. So that's where I said, thus the mechanical initial energy initial was higher than my calculated value. So I observed. So that's now going on to further explain more clearly how this led to the cause. So I say I get 2 of these points, 2 out of 2. And then part E, so they asked what is a possible reason for a decrease in the energy during the experiment? And then they said, include references to conservative and non-conservative forces. So here's how they have awarded points. First point for identifying a reasonable cause for the decrease in energy related to the non-conservative forces acting on the system. So yes, I indicated friction, that it was a non-conservative force. So if I stopped there and said, non-conservative force, force of friction, and I stopped, I would get 1 out of 2. Okay, now you had to go on and say some more physics about how friction results in a decrease in the energy. So that's where I went on with the work energy theorem. So I think I got 2 out of 2 there. So I think I got 15 out of 15, despite the leaving off the electronic balance, that little mistake. It didn't look like I got penalized. I got 4, 10, and then another 4 is 14, and one more is 15. 15 out of 15. Okay, so that is an example. Now, I just want to show you that there are other procedures than what I had, and they give a couple more here. So let's take a look. Again, hopefully you could see this because it's pretty small, but I wanted to fit on so we could see both. So what they had in one example is a car on a flat surface in like a multi-body problem, and this goes down a certain height and accelerates the car. So they said use the electronic balance to determine M and MB, the two masses, attach the object to the cart using the string. So they have this, place the cart on the track and hang the object so that the string passes through the pulley. So then we've got everything all set up. Allow the object to fall a distance h from its initial position to the floor, using the meter stick to measure the distance fallen. So again, using the meter stick. Again, a lot of people say, let it fall distance. And they might not say h. Or they might say, let it fall distance h. They didn't say use the meter stick, right? You got to say those things, even though it sounds tedious. Again, use the stopwatch to measure time, t, all those three things it takes to fall the distance h and measure h of the table. So there is that procedure. And then for grading, let's see. Yeah, so then another possibility is they had the object go down an incline and accelerate like I did, but they measured the time it went a certain distance down the hill. Now, in both of these cases that they have, you cannot use v equals distance over time because that gives you the average velocity. So here is why they had to say acceleration is constant, so d is the average velocity, the original plus the final divided by 2 times time. Therefore, with v0 being 0, then solving for v final, moving the 2 over and the time over, there's the expression for the final speed. Not distance over time, but 2 distance over time. So, just a couple different procedures. Obviously, these are open-ended, so there are many ways you can answer many different kind of procedures. You just have to go through when you're practicing and make sure that you hit all the points here, okay? As long as you do that for your particular procedure, you'll obviously get credit. Okay, so there is a free response question and a possible solution. What I want to do now is continue on because this was just like a one trial kind of experiment. I measure the height, I calculate mechanical energy, I use distance and time, and I calculate mechanical energy, and I compare them once. But that's kind of a subpar experiment because, as you know from any kind of measurements, the more measurements you make, the more accurate your results become, kind of like doing averages and things like that. One measurement is subject to a lot of error, whereas an average is a more solid result. So very often what we do is we measure a whole bunch of data and not just take averages, but what we do is we analyze graphical trends. And we have this little trick that we learned, how to make straight lines out of curved lines. And that's what I want to focus in on now, because a lot of these questions, you'll see, they say, generate a question and create a graph. Or sorry, generate a procedure that generates a graph. Here's words taken from one free response problem. It said, quote, the students are expected to find G by plotting data in a graph. Okay, so it tells you right away you're going to have trends in the graph. But the problem is not all trends are straight lines. Like, for example, the last experiment I had, let's suppose I was measuring the velocity versus height. So this is the independent variable. I could put the car as high as I want, and as a result, it has a velocity at the bottom. So this is going to be on my x-axis. If I do graph that data, you could see that because of the v squared, I get a graph like this. It's actually a square root graph. There's a trick to make that into a straight line. What you could do is solve for v squared, and then the formula, if you divide out the mass is gone, and multiply the 2 to the other side, you get v squared equals 2gh. I put parentheses around the 2g for clarity. Well, I'll explain that a little bit later. So what I could do is, instead of plotting v over here, I could plot v squared. See how there's a v squared over here? So make that the new y-axis. Okay, so you see that this now is on the y-axis. I make an entirely new column of v squared terms. So for example, 1.4 x squared is 1.96. 1.9 squared is 3.61. Yeah, okay. 61. Okay, and then 2.4 squared is 5.76, and 2.8 squared is 7.84. So there it is. All the velocities squared. I make a new set of numbers here. What I then do is I plot this on the x-axis and then this on the y-axis. And when I do that, it's a little trick, the data comes out linear. Now, this is of the form y equals mx plus b. The term in front of what's on the x-axis is the slope of the graph. So if I calculate the slope by doing rise over run, I get a certain number. I could see that that number is going to be 2g, g being 9.8. So this term in front is the slope. And therefore, if I have the slope, then I can divide it by 2 and I get g, right? If I just divide both sides by 2. So g, 9.8, will be 1/2 the change in y, which is change in v squared, over change in x, which is change in height. Pick a couple points on the line, get the answer, and take half of that, you should get 9.8. Okay? So, now, let's suppose I had to come up with some sources of error. I already mentioned how to do this a little bit on the last example, but I want to go into it in more detail in this particular case. So let's suppose, case 1, I do this experiment, I make the straight line, and I get an experimental g less than 9.8, like for example 9.2, okay? So then the question asks, come up with a reasonable source of error. So what I might write is the quotes of what I would write. The slope is too small, right? We could see that right from here. Why is this too small? The slope is too small. So then I look here and I need to, so that's like the one point, right? Now I need to go further and say, well, how would that impact the results? How did that possibly happen? So I could say force of friction causes negative work. Work net is delta K. That results in a reduction of the experimental velocity, right? And so all these points shift down. You know, I would continue on. All the points shift down, and therefore the slope got too small. Okay, so that's one possibility. Another possibility is maybe instead of the velocity being too small, the height was too big. Now here's the tricky thing. A lot of students will say, oh, I know why the height was too big. That is not sufficient. Why isn't that sufficient? Because there are actually two heights. There's the true height, what it really is. And then there's the height that you measured. When you say height is too big, you're not saying which of those is too big. Is it the height you measured that's too big, or the height that's the actual height is too big? Give you an example. So here's the diagram. Let's suppose, for whatever reason, I don't know, you measured the height over here, okay? So the measured height is too big is a correct source of error. What that would do is it would make all these bigger values. So all these points would shift to the right, which would tilt the line like that and make a lesser slope, giving you a lesser g. Measured height is too big. However, it could happen that maybe instead of measuring here, you lifted the car too high instead of measured too high. The actual height the car lifted is too big is the wrong answer, because what that means is that these h measureds are all smaller than they should be. And if they were all smaller than what they should be, and you keep the y values the same, but you decrease the x values, that shifts the line with a greater slope, giving you a greater acceleration. So Height was too big, not enough. Always say, is the measured or the actual of a particular piece of data too big or too small? Okay? Another case. G experiment is greater than 9.8. This happened to you a number of times in experiments where you got, instead of 9.8, some people got 11 in experiments. So you can't say force of friction, right? That would make the... another thing people say, oh, sometimes, oh, the bearings were greased up, so the friction was reduced and we had more than 9.8. No, if with no friction, you would get 9.8. How do we get more? So here are some possible explanations. You could say the slope was too large, obviously, right, from this formula. And so why? You could say the actual height we lifted the car could have been higher. A smaller h measured in the calculations increases the slope, increasing experimental g. Right? So now the actual height was too high, so all these ended up being too small, which would shift the line upward if h's get too small. Another possibility. I could have accidentally pushed the car forward as we released it, increasing all measured velocities. So, you know, you gave it a little shove when you let it go. So all these velocities should be bigger, meaning all the v squareds should be bigger, right? And that shifts the line up and makes a greater slope, greater than 9.8, maybe 11. Okay, so again, the conclusions, the data, you have to be consistent, explain away too big or too small with the right effects on the variables, and then be very careful about being very explicit with what exactly is too big or too small, experimental or actual. All right, so let's see. Covering. Okay, so let's suppose we got another example where we accelerate a car and we measure the x coordinates and the time. So as a car is going down, it's getting faster and faster and going further and further as time goes on. If you look at x equals 1/2 at squared, which is the theoretical relationship between time and x as something's accelerating, that's a parabola because of the t squared. So how do we linearize that so we can analyze for acceleration? What we could do is we look at the formula, it's got a t squared, so we're going to calculate a new column of t squareds. Take all the times that we actually measured in the experiment with a stopwatch and square them all. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. And that's our new x data that we plot. Not these original ones, the new ones with the x coordinates that we had originally. So x on the y-axis and time squared on the horizontal axis. From y equals mx plus b, we could see if this is on the y-axis, this is on the x-axis, this term in front is the slope. So the slope is half the acceleration. So if you want the acceleration of this car, calculate the slope of this line, make a nice big triangle, rise over run, not using data points. The slope of the line. Multiply it by 2, you have the acceleration of the car. I'm going to skip sources of error discussing because I hope you have that clear now, how to analyze if this is too big or too small. We're going to go on to the next example. Okay, so simple harmonic motion is not in the on the test in 2020 because of the COVID-19 closures. So again, you're not going to study this year. Future years, students will be studying this, but not this year. So this is the relationship between, if you measure masses in the period of oscillation of a mass on a spring as it's going back and forth, you're measuring the periods, you would get this because of the square root. So kind of like the example I had before. So how do we turn this into a straight line? What I could do is I could square both sides, and that gives me t squared 4 pi squared. The square root goes away, and I'm going to lump the k with the 4 and the pi squared, leaving me m here. So again, this is the original data. I create a new column of t squared. So this time I'm squaring what's on the y-axis, not what's on the x-axis over here. And if I plot t squared on the y and mass on the x-axis, I'll get a straight line. This is y, this is x, straight line. And the term in front of what's on the x-axis is the slope. So the slope of this line, when you calculate it using rise over run, is equal to 4 pi squared over k. And that's what we want to determine k. So if we move that to the other side, divide by the slope, we have the spring constant of the spring is 4 pi squared over k. 4 pi squared over slope. And the slope, of course, is change in t squared over change in mass squared. So I go ahead and calculate that. Sources of error again, this time I went into it. So let's suppose the experimental spring constant was too large. If you look at this formula, you can see that means the slope here was too small because it's in the denominator. So it's smaller than what it should be. So how could this be too small? Either this is too small for some reason, or this is too big. Either of those would result in a spring constant that was too large. So then you might have to come up with some kind of reason. Why was the mass too big? Maybe you ignored the hook that held it in place, okay? And so, that would be the other way. So the measured masses were too large. Maybe you used the pan over and over that it was extra mass when you measured. Some reason, right? You got to come up with a reason. Another possibility, let's suppose the experimental spring constant was too small. How could that happen? This must have been too big. How could this be too big? Either this is too big or this is too small, right? And again, you would have to come up with some kind of reasonable reason why those variables were error in the way that they were. Okay, I want to point out that in this example, there is another possibility. Instead of squaring both sides, you could have simply plotted t on the y-axis and then done this and create a new column of, instead of t squared, but the square root of m. Take the square root of all the masses, create a new column, put that on the x-axis, and that would also be a straight line, with the slope now being this. Okay, so there are other ways, other possibilities, okay, other ways to linearize the data. I'm just showing you some simple ways. I'm going to show you two more examples. Put this here. Okay. Okay. Again, in 2020, gravity, force of gravity is not on the AP. Future years it will be, but not in 2020. So, let's suppose you do an experiment where you measure a bunch of force of gravities, a bunch of distance, and you determine G. And obviously what I'm talking about is two masses, and you measure the force of gravity, and then you start separating them, and you keep measuring the new force of gravity for each of these distances. I just made up some data, you know, but you have a table, and it's going to obviously be longer than just 3 terms. So if you plot this with force of gravity on the y-axis d, the distance on the x-axis, you get a graph like this, okay, and inverse type of proportionality. So what we could do is, we don't really need to manipulate our formula too much. We just need to separate out the 1 over d squared, leaving the g and the m alone. Now what I do is, if I put this on the y-axis and I create a new x column with 1 over d squareds, that will create a linear graph. So what I would do is, for example, 1 over 1 squared is 1. But if I do 1 divided by 2 squared, well, oops, wait a minute. 1 divided by 2 squared, I get 0.25. I could do 1 divided by 3 squared, right? 1 over d squared, and I get 0.11. 1 over 4 squared, right? So on and so forth. I make a new column, 1 over d squared. Now what I can do is I can plot this on the x-axis, and this on the y-axis, and that will give me a straight line. My data points will rise linearly. I do a best fit line, I do a triangle, I create the slope. And then what does that slope mean in terms of the original data? Well, if you look here, y-axis, x-axis, this is the slope. So slope is g times the two masses of the two objects in my experiment, right? So if I were looking for g using all these data points, then I just divide the slope by the two masses and I have the g. And it should be, of course, 6.67 times 10 to the minus 11 Newton meters squared over kilograms squared. And then it might not be, and you might have to come up with sources of error. Okay, so that's another example. Final example. So we're doing an experiment with force of friction that's proportional to velocity. And we measure velocities at different times as a car is slowing down by air resistance. Earlier in the year, we derived this formula. The velocity decreases exponentially. So if we plot the data points of different velocities at different times, the points will be going down in a curve like this. And so we can't really easily analyze that graphically, unless we do something to the formula to make it a linear trend. We need to get rid of the exponential. We do that by taking the natural log of both sides. Ln of v, and then the ln of all of this. But when you have a ln, a product inside the natural log function, you could take the log of this plus the log of this. So that's where we get the ln of v0 right here. And then the ln of e to the negative b t over m, ln of e just gets rid of the e, so what's left is just the argument in the exponential, negative b over m times time. Okay, so this now is an equation of a straight line if we put this on the y-axis and time on the x-axis. Okay, so we create a new column, take all the old velocities and take the natural log of them and create a whole new set of numbers. Put this on the x-axis, this on the y. So there's the x, the time, and then the ln of v on the y-axis. Those points straight line with a negative slope, as we could see here. So y equals b plus mx, right? So this then is the y-intercept right here is ln of v0. You could take this right off the graph where your line crashes into the y-axis, and maybe it's, 8.7 or something, and then you set it equal to ln v0, solve for v0, and you get the original velocity according to the trend data. And then the purpose was to determine b, that constant in the force of friction. We could see that the slope of this line, y equals b plus mx, b, the slope is negative b over m, okay? The slope here, okay? And so you calculate this slope, you set it equal to there, or you could solve for b by multiplying negative m to the other side, take the slope, multiply by negative mass of the object, and you have that frictional constant b. So that is those are some examples of how to linearize trends. So pretty long video. Again, a recap. I solved an AP free response problem where I had to design an experiment. You have to check off equipment you need. You need a diagram that has all the parts labeled, as well as whatever distances you can, label those as well. When you write a procedure, state every time what you're using, what you're doing with it, and put a symbol for that quantity, right? So again, stopwatch, what I'm using, I'm measuring the time with it, and the symbol T, okay? And then, these will change calculations depending on the type of question, and then source of error. Make sure you're explaining away things correctly, what is too big or too small, and remember, don't just say height is too big, say is it the measured height or the actual height. Be very specific when you come up with sources of errors. And then a whole lot of examples of how to make straight lines out of curved data. Okay, you basically realize that a straight line has this form. And you try and get your function somehow to take this form by squaring variables, taking the log of variables, reciprocals of variables, all kinds of different techniques to get these lines to go straight. Okay, so hopefully you'll do well on the question now of designing experiments, how to analyze graphical trends, and how to come up with sources of error. Thank you for watching, and maybe there'll be another video. If there is, then I'll see you in that next video.